Hey, welcome back. Good to see you again. Thanks for joining the channel. Today on the bench, I'm going to be doing something a little different. I don't know if it's going to be, it won't be a repair, not on a piece of audio equipment. But what you're looking at here is my distortion and noise meter. This is AWA F242A. I picked this one up on eBay. I did repairs on it. These switches were really dirty. I needed to go through and do cleaning and bring this thing back to working condition, and it works great. Now I use this mainly right now for doing FM alignments, the FM discriminator. I can align it to the lowest distortion and it works really well for that, and I enjoy using it. I want to use it for amplifier measurements as well, for measuring amplifier distortion, but I'm not set up for that yet, and I'll show you why. Right now I'm feeding it 1000 hertz tone into the input off my signal generator, and that's what I'm going to be using, my junky Chinese signal generator. This thing's works good, but it's got high distortion levels, and let's read it right now. It's 1000 hertz tone coming out at 1 volt, and I'm feeding directly into the distortion meter. So to set up the distortion meter, you have to put it into the calibration mode, which I have here. And what you do is you calibrate it with this knob. You can set it, and you set it for full scale deflection on the meter. And I think that's it there. And then all you need to do is press read on the distortion, and it reads out your distortion in percentage or decibels or volts. Now if I look at the distortion of this signal generator, let's turn this up. We're at 3% distortion right now, 3% scale. So if I look here, 3 is this top scale, and I got just about 0.75% of distortion. Let me zoom in on the meter so you can see it better. So let me switch ranges here. I'm going to go to the 1% full scale. So we are reading 0.72% distortion on my signal generator here, which is pretty high. You can't really use that for any meaningful measurement on an amplifier, because most amplifiers are way below that, probably 10 times below that rating. So this is quite a high distortion on my signal generator. So what do I do? Okay, so one of the features of this distortion meter is it has an output, and I can feed this output into my scope, and we can visually see the distortion, so we can see what kind of distortion we're dealing with here. So that's exactly what I got going on here. I think you can see it on the screen. I have the scope up on screen. Okay, so now we have this in calibration mode, and it's expecting to see a signal from 20 hertz to 20 kilohertz fundamental frequency. So that's what I'm feeding in here on 1 kilohertz signal, and it's on cal right now. So when it's on cal, you use this control to set the meter to full scale deflection, and that calibrates the internals for the level of signal you're feeding it. So right there. When I press the button to read, what this device does is it has an internal oscillator, a really ultra low distortion internal oscillator that locks to the incoming signal. And if I switch frequencies, let's see here. If I switch frequencies, you can hear the device inside calibrating and reconfiguring to set up that internal oscillator. You hear the relays clicking inside. But that doesn't concern us. What it's doing is it's setting up an internal oscillator, ultra low distortion internal oscillator, and it has its own signal of the frequency we were sending it in. So what it's doing is comparing our signal with its own signal, and it's doing a subtract, and it's displaying the output on our scope. So let's turn this to read, and then right away we can see our distortion. We can measure it. This is 3% full scale. I'm going to turn it to 1% full scale, and we are up over 0.7% total harmonic distortion are actually about 0.71 or 0.72, actually 0.73 actually. That's what it looks like here. Quite a lot of distortion. If you look on the scope, you can see it's mostly made up of a second harmonic. That is twice the frequency of our signal is feeding in. Top trace is our signal from the signal generator. Second, the bottom trace is the output from this distortion meter. That's what the distortion looks like after it's been subtracted. Not very good results for that signal generator. The signal generator is great for just providing quick and dirty signals, but it's not a high precision, low distortion generator. It's got quite a bit of distortion, as you can see from the oscilloscope screen. So we can't use this for doing amplifier tests. This is just no good. It's not sufficient. That's where this comes in. This is a Heathkit model IG-18 sine square wave audio generator. Now this one promises to have low distortion on the sine wave, and then it takes the sine wave and it creates a square wave. We're not interested in the square wave, so I'm not going to talk about that at all. But we are interested in the sine wave capability of this generator, and it promises to be quite a low distortion one. So I picked this up on eBay. I can't remember what I paid for it, but it was reasonable, and it's in pretty good shape. It looks like it was owned by maybe a ham guy, because you know, it came with a book. It did come with a book, and it's very comprehensive. This one was built from a kit, so you can see the check marks when the guy was building it. He did a very meticulous job of building it. I was going through and reading his notes and all the notes he made for himself, and he did a good job putting it together. I haven't looked inside yet, but from what I'm looking at here, it looks like it was well built and cared for. So we're going to test this one out, see how well it does on a distortion meter, if it comes up to its claim. Let's look at the specs and see what the claim is for this. Okay, lots of specifications here, yada yada yada. I'm really not really interested in its frequency ranges and stuff like that. And meter output, meter range, 5% on the meter, who cares? This is the one we're interested in right here. Distortion, less than 0.1% from 10 Hertz to 20 kilohertz. Okay, so let's measure this with my distortion meter and see how close it comes to that 0.1%. That is still 0.1% is still fairly high in this modern world of electronics, but it's still a hell of a lot better than my other generator. So let's, like I said, let's try this out and see how it fares up. Okay, I'm wired in, and let's turn this thing on. And right away, we are sending out a signal. I got it set up for 1 times 100. 10 times 100 is 1 kilohertz. 0, so that should be our 1 kilohertz. Let's turn up the amplitude. Let's see here. Let's turn that down. Let's turn this up. Let's give it so much signal. Let's give it that much signal. Maybe a little more. You can see it up on the scope there. Now, let's do our distortion reading. Alright, so let's set up for calibration. So let's turn this up and set this to full scale. Right there. Okay, let's hit read. And let's turn up our scale. 3%, 1%. I'm on a 0.3% full scale, and we are measuring just over 0.1%. So this here is 0.1%, this is 0.2%. So we are probably 0.1, 0.14 or 0.13% distortion, which is considerably lower than on the other one. We are doing actually pretty good. And if you look at the distortion on the scope, you can see it. The little squiggly line there, it's not quite there. So that distortion that we're seeing on the scope suggests to me maybe this generator might need a tweak, maybe might need checking over. It might have a fault inside, it might have old components that have drifted, might have old caps, resistors out of tolerance. This thing is actually from the late 60s, if you believe it or not, and early 70s, so that's how old this thing is. So if this is all original, we're going to have some problems with some of the parts inside. I'm pretty sure of it, I'm going to guess. So let's have a look at this and see what we can do to help improve it. We got our baseline measurement of 0.1. I'm going to call it 0.13 because it's drifting. And it's settling on 0.13% distortion. So that's what we got as our baseline. Okay, got it unplugged. Let's pull the lid off. First time I've seen the inside. Wow, look at this thing. Ooh, it's got a real smell of vintage electronics too, coming out. Quite interesting. Whoever built this put a lot of care of attention into it. But we still have really old capacitors. And my main concern is all these carbon comp resistors. They could be super drifty and might cause us some problems. So what I'm going to do is get my ohm meter out and check a lot of these resistors in the amplifier or the oscillator circuit. Power supply, well, look at these old caps. These are not great caps, that's for sure. Neither are these. So I expect probably need a few caps and some resistors. Very nice. It's well built. It's got some precision components here. 2% capacitors. They're all 2%. These resistors here are all 1%. So I noticed the potentiometers are clean and then switches are working, so I'm not going to waste a lot of time cleaning switches and pots. But I do want to get after these resistors to see if they are behaving the way they should. So let me get my ohm meter out and start looking. Yeah, and just as I suspected, we have some bad components here. Let's see here. Alright, so this is supposed to be 1.1K. That one doesn't measure. Another 1.1K. Here's 150 ohms. Reads 171. 10K reads over 11. 1.1. Almost 1.2. What is this? Brown, green, black. What is that? 15 ohms? Almost 16 ohms. This one doesn't want to measure. 2.4K. Yeah, 4.7K. Yeah, I can't read these when they're in circuit, so I'm going to have to lift some of these up. Here's another 150. That one's way out. So I do have a lot of resistors here out of tolerance. Even though they're 10%, they're still farther out than 10%. I think I might just blanket replace all these resistors. They're all carbon comps and put metal film in. I think that's where we're going to start. And then these caps. What is this then? This cap is 250 microfarad. I'm going to measure these as well, but I have a feeling they're just going to get replaced regardless. I want to bring this thing up to a good standard that I can use and I can trust. What is this one? 30K, and it's supposed to be 27K. So that one's over 3K out, almost 4K out of tolerance. Here's some 82K resistors, reading 87. 93. Yeah, these resistors all have to go. All right, I'll warm up the soldering iron and get started on these resistors. So whoever built this thing took a lot of pride in their work, and it's really really nice job they did on the soldering and the lead dress, everything. It shows that they took a lot of pride in it, and it's kind of a professional result here. Nice soldering on the printed circuit boards. Everything's good. Really pleased with what we're getting here. I picked this up, like I said, on eBay, and I really had no idea of its condition, if it was working or not. Not that I was bothered with it, but you know, if it wasn't working, I was going to fix it. But we don't need to do anything. It's completely functional, and it looks like it hasn't been touched since the day it was built, which is good. But the bad part is we have all these old resistors that are really badly out of tolerance now. That's the bad part. So we're going to go through and replace all these resistors, even these ones here. What is that? That's a 620 ohms. Oh, that's our 600 ohm. Okay. Yeah, really nice job. Well done, guy. Wherever you are. Okay, just going through replacing resistors. There's quite a few of them out of tolerance, and I am replacing every one that is not spot on. A lot of these have drifted out. Like these 10K resistors all measured around 12K. So that's an example. So they all got replaced. A lot of these 1.1K resistors are out of tolerance too. They all read up around 1.2K. Now I don't have 1.1K. It's not a stocked resistor. So what I'm doing is I'm trimming them, adding resistance on the back to trim them out to 1.1K. These are 15 and 18K resistors, and I measure and calculate what I need and tack it on the back, and now these are 1.1K resistors. Spot on. So that's basically what I'm doing, going through and making sure everything's 100% in the circuit. These caps, 1969 date codes on them. They measure out around 350, 370 microfarad. I bet you they have a lot of leakage too. If I put them and check them, I'd probably get a lot of leakage. These ones the same thing. These ones are 250 at 35. These measure up around 370, 330. So they're really far out of tolerance. Not that it really matters if they're just power supply filters, but I want to make sure everything's 100%. And yeah, I go through the power supply and the main circuit here, and I'm also going to be checking a lot of these resistors that are tacked on the switches. There's quite a few of them here. Go through and make sure they're all 100%. So I'm just plugging away, and I just thought I'd give you an update. Alright, just going through and trimming all these resistors or replacing them if I can. These resistors are way out. This one's blue, red, brown, gold, which should be 620 ohms, 5%, and it reads 665 ohms, so that one's out of tolerance. A lot of these, I replaced this one already. This one here is 150 ohms. It was reading up over 200. Here's some more. This is 1600 ohms here. Well, that one might not be able to, depending on how the switch is. I can't read them. I have to remove them from circuit. Those ones are shunted. They're all shunted. There's a chain of them here. They're probably all out, and I have to replace them all. Here's a 750 ohms. Can't read it. 1100 ohms hidden in here. Yeah. This is the range switch for the amplitude on the output. It's not critical, but I want to replace these resistors because they are out of tolerance, and it really messes up the amplitude as you switch from different ranges. So I'm going to make sure they're all accurate as can be anyway. This one here is 2.4K, red, yellow, red, and it measures 2.6K. So that one's going to be trimmed. Yeah, so I'll just keep plugging away. I got a few resistors on this switch here, 3, 5, and I'll fix those up as well. The rest of the unit's been replaced, either replaced or trimmed, the resistors, and they're all good. Caps are changed. Went through and checked these caps, they're all good. I'm not touching these 1% resistors. A couple more up here that were replaced. Another mod I'm going to do is I'm going to add a capacitor to the meter to slow down the movement on low frequency measurements, and that's easy. I could just add a 220 at 6.3 volts here, right here at D and E where the wires come to the meter, and just tack a little capacitor in there. And we'll just get this thing going. I want it to be a good signal generator for producing audio signals for amplifier testing. So let me finish this and I'll bring you back in. Okay, I'm going to give you a little demonstration here. I always harp on about these carbon comp resistors. Here's a resistor. This is a brown, green, brown. It's silver band. That is 150 ohms at 10%, right? So it should measure between 135 and 165 ohms to be within that 10% band. But let's check it here and we'll see. I'll show you what it measures. It measures 181, which is 20% out of tolerance. Okay, now you might not think that's a big deal, and it is on tube gear. It really isn't a big deal, but for solid state components, solid state electronics, it is a big deal to have it this far out. Now I'm going to show you what happens when I apply heat to one of the leads, as if I'm soldering on it. Okay, so I'm going to heat this lead up and watch the actually what I'm doing is heating this resistor up. And look how temperature unstable it is. It's already up at 190. And when I remove the heat, it cools down. Actually, it's not at 180 anymore. It went to 174. It's cooling down. Okay, so let's apply some more heat. This is why you don't want these carbon comp resistors, because they drift so much with temperature. Heat it up again. Give it a good soak of heat. And you see how much this thing's drifting? Just let it cool down. Now it's reading 170 ohms. So why is it changing? Why is it different? I measured 180, now it's 170. Well, that's the problem with these carbon comps. There's no predicting on what they're going to do in the future. They could go up in value, they could go down in value. When you heat them, they change in value. When you cool them down, they change in value. So that's why I advocate just getting rid of them, because they can cause a lot of problems in your circuits. Look at that, eh? I'm thinking maybe what I did is I drove out some of the moisture that was in this resistor, and maybe it's gone down to more of a stable value. We could do it in any resistor though. Pick out any one of these. Here's a 82K. Let's measure this 82K. It's measuring up around 95K. So how far is that out of tolerance? Quite a bit. Let's heat this one up and watch how it drifts. This one's going up in value instead of going down. Look at that, it's over 100K now, 110. Just crazy, crazy. 120. 130, 140, 150. It's almost twice what it should be. So let's let that cool down. Cool this thing off. Okay, so now we're still over 100K on a resistor that should be 82K. And it's going to stay there. Now if you're just soldering this in a circuit or something, or maybe you wanted to make a change in the circuit and you were soldering on it, and that's how much it would go out of tolerance. And if I do the calculations, let me see. So this resistor is now 27% out of tolerance. And it's got a silver band, so it should only be 10%, but that's, you know, that's garbage. Okay, we're all back together, and we're up and operating again. And now I need to go through a full alignment. So I have all the instructions here in the book, and I'm going to be using a scope. I'm not going to videotape any of this because it's pretty well laid out in the manual. If you have the manual or a PDF of it, you can read it all, and tells you exactly what to do. I'm going to go through and follow the steps and set this thing up, and then we'll come back and we'll do some measurements. Alright, now final test is we're going to see what the distortion figures are for this generator. Let's set this up to turn this up to about 1 volt, and let's calibrate this. Okay. Alright, so what do we got? It's like we got I'm on 0.3. Okay, so our distortion has improved. We are now down 0.07, I would say, because it is under 1. Let me see if I can turn on some filters here. Turn on a high filter. Doesn't change. A low filter. Doesn't change. And then a weighting filter drops it quite considerably. Drops it down to 0.05% THD. That's an improvement. So let's see here. That's working good, I think. The weighting filter. I wonder what that does. It's a bandpass? I can't remember. I know this cuts below 400. This cuts above 20 kilohertz. Now I'm wondering if there's any adjustments or anything that we could do to make that noise figure or that distortion figure go down. Let's see here. I'm just playing with the frequency a little bit. Just this is how sensitive these oscillators are. Turn it right down, and we are still at 0.775 or so. Okay, let that settle. Yeah, no change. That's good. I think for what it's worth, this might be useful for measuring amplifiers. If we're down in this low, actually I could go even here and measure this. This is 0.07 5 or 4. So here's a look at the schematic. Here's the power supply. Pretty basic. It's got 2 primary windings that can be configured to 120 volts or 240 volts, depending on how you wire it. And this secondary full wave bridge rectification. We have a pi filter here. We got a capacitor, dropping resistor, capacitor. And this is typical of old tube radios, tube amplifiers. They have that pi filter in it. I upsized these capacitors to 470 microfarad instead of 300. And then it's just a series pass regulator with a Zener diode regulation. This one here, this capacitor here, stabilizes the voltage on the base. And then output, we should have 43 volts. I measured 40.1 or 41 or something. So it's out a little bit. This diode is probably getting tired. Maybe the transistor's tired too, I don't know. But it's working. I'm not going to play around with it. Now if you look at the schematic for the wave generator, it looks very suspiciously like an amplifier. You have your output devices here, and you got 2 emitter resistors. This is your output. So you have an PNP and NPN. Here you have long tail pair. That's providing, allowing for feedback. So we have a feedback loop that comes down here, and it goes into the switched circuit. It's a notch filter. And if I zoom over here, it shows you all the configurations for this notch filter, depending on which position it's in. So what they're doing is they're switching in and out a capacitor. We have 5 microfarad, 500 nanofarad, 50 nanofarad, 5 nanofarad, and 500 picofarad capacitor. They're arranged that way. And then we have decade resistance here and here, these resistors. So that's this notch filter here, and these, as you click through the resistance range, or as you click through the ranges, it switches out different resistors and capacitors. So that sets the timing constant for this circuit. So it's a feedback circuit. Feedbacks into the input, and we have negative feedback on this side. Hopefully we keep distortion low. And we have a bias spreader, and this looks like a voltage amplification stage right here. So it looks suspiciously like an amplifier, but it's used as an oscillator. This part here is Schmitt trigger. This is what takes the signal and squares it off into a square wave, and then we have output on this side. Pretty basic, but hopefully, you know, it's low distortion and it works well. It's very simple, not much to go wrong with it. Okay, I did some measurements, different frequency bands, and the worst one I got was at 50 Hertz. I got 2.25% THD. Now I don't know if that's correct, because after I came back and redid it, it dropped to 0.086%. Now I think it's just because this is the first one I did and the machine is cold. I don't know. And then I was measuring 100 Hertz. It was pretty high. It was over 0.1%. 1000 Hertz was over 0.1%. And then when I got to 5000 Hertz, it dropped quite a bit. And throughout the range, pretty flat. That highest my distortion meter can read is up to 24 kilohertz, and it was still at 0.06. Now I went back and redid some of these, and then these ones were now lower. These are down in the 0.07 range. So this one was like 0.08. So they improved, so I think it just had to warm up. That's what I'm thinking. But it's still high. What is the spec on this thing? So this is the spec here. Distortion, less than 0.1% from 10 Hertz to 20 kilohertz. And I wasn't getting that. Not when I first turned it on. I was not getting 0.1% throughout the band. But I'm getting it now. So I'm wondering, I'm thinking of I'm still getting noise in the distortion in the signal. Now I measured bias across these resistors, or the current across these resistors. This is 107 millivolts, and that equates to about 7 milliamps of current through these output pair. I'm thinking of maybe playing around with the bias, adjusting it, either spreading it apart, or no, I want to turn the bias up, so I want to turn up the current on these two transistors. I'm going to play around with some values, maybe add a potentiometer, I'm not sure. Also want to play around with some of the feedback here, maybe change a few values and see if I can get the distortion lower than what it is now. So I have this realistic, it's an ST or SA 155 integrated amp. I use it as my bench amp, only because it's super cheap, it's easy to use, it's small, doesn't take up any bench space, and I can just plug an input in and connect the speakers up. It's very plug and play, and but I don't expect this to have very good specifications. This has power amplifier chips inside. I think there's two, one for each channel, and I think they're pretty high distortion. So let's see if we can get a measurement on what this thing does. Okay, let's see if we can measure this distortion of this amplifier. Let's set it up. I got my tone generator connected, and I let it warm up for at least half an hour. I noticed that if you let it warm up half an hour or so, the distortion level will drop over time. So let's set this up for 0. I'm having a hard time reaching around the camera here. Let's set this to 0. I think I got it. I can't see. Yeah, it should be pretty close. Right here. And let's measure. And for what we're measuring, we're at 0.0. We're at 0.1 full deflection. So on the 10 scale, we're reading approximately 8.3. So that would be 0.083% distortion. So let's connect up the generator. I don't know if you can see on the scope, you can see our signature for the distortion on the bottom trace. I see a spike going on right in the zero crossing of the sine wave. There's a big zigzag spike. So I'm wondering, what can that be improved on? I don't know. But let's connect up the amplifier now and have a look. So just bear with me while I reconfigure everything. Okay, we are now through the amplifier. Let me adjust the volume control. See, when I touch the volume control, we can go into clipping, back it off. We don't need it so high. I'm into an 8 ohm load as well, so let's take it to about this range here, and let's adjust this. So that one's pretty close. Let's try this one. Okay, now you notice there's quite a phase difference on the two, before and after the amplifier. So let's put read here and read what we got for distortion. Let's see if we can read this. Now, what does it say here? It actually says lower than what it was before. So we're at 0.061. How does that work? That the distortion goes lower through an amplifier. Look at the mess that's coming out of it, though. It's interesting. If I get rid of the high filter, the weighting. See, it's quite twitchy too. Wonder why it's twitchy. Let me do this at a lower. Let's see, we are pretty high up. Let's do it right here. Let's try this. Okay, so we are 0.3. So our distortion now is 0.11%, and it's fluctuating quite a bit. Looks like we're getting a lot of hash and noise coming in too. Get the volume turned down. Let me go near clipping again. Let's take it right about here. Read. And we are down. We are down quite a bit. We are at 0.073%. So level does play a factor into this. I'm not sure if this setup is very good for measuring distortion. Let's see what our level is here. We're on a 10 volt scale for voltage. So we're right just below 4 volts RMS. Maybe we should do our measurement at 1 volt RMS. Let's do that. One volt. Right there. Okay, that's going to be our level for testing. Got to compare apples to apples, right? So let's go here and let's adjust for right there, I believe. Okay. All right, there it is. That's what we should be measuring. And we're getting 0.08 plus. It's really twitchy. Well, there you have it. Mainly this is just a big experiment for myself to see if this would work and for what fill my needs, for what I want. I want to be able to measure distortion on amplifiers. I have the meter, the distortion meter. I just need a good clean sine wave source. And I bought this one, tested it out. It was kind of iffy. Did some work to it. We did quite a bit of work to it actually. Replaced all these parts, all these caps. Oops, and all these resistors. They all got thrown out because they're out of tolerance. And things improved quite a bit. But we're still finding that it's not really working for what I want. It's not providing a low enough distortion-free source to check amplifiers. You know, a lot of the big problem I'm having is my cabling and my connections and bench noise. Bench noise is a huge thing when it comes to measuring distortion levels. You're getting, I'm getting RF interference all around this bench from all the devices that are plugged in and maybe not even turned on. They could still be radiating garbage into the air. But I'm trying to figure out a way to get this so that I can set up and do distortion measurements on amplifiers. Now I did go a lot farther with this. I actually went in and I replaced a bunch of transistors. I did some modifications to the power supply. I did a number of modifications, and actually I got the distortion down to below 0.05%. And I'm pleased with that because I think this might have potential. I'm not sure. I still have to do more bench time on it and playing with it and working with it and learning. Learning is the big thing here. Learning what works and what doesn't work. Now I did, like I said, I did go through and make some modifications. I changed transistors. I changed a few other parts around. I still have some more plans for this, and I did film more of this, but I'm not going to include it in this video. I think this video's gone long enough for what the purpose I'm just trying to convey here. But I do want to continue on this. I need to move this off the bench because I got other things I need to do. So I'm going to end this one here. Thanks for watching. Comment below if you have spotted stuff I'm doing wrong and I point it out to me so I can correct it, and maybe I'm doing stuff wrong here, I don't know. Some of you guys will know maybe more better than I do. Alright, thanks for watching, take care, and we'll see you on the next one.